Cantavicaria, my boss, David Rustling, the Linaro CTO, which means I get to be involved in a variety of technologies, the most recent being high-performance computing, HPC. Furthermore, being in the office of the CTO means we have to push the boundaries. So as a result, this is no ordinary talk. So get your devices together, scan the QR code, go to the URL, linaro.co/HPCX. Yes, this talk will be different. Linaro is all about collaboration, and this keynote will involve just that. Now, this is a picture I'd like to take of the audience scanning there. This hasn't been done before at a Connect event, which makes it risky and all that more exciting to do, I say. If you can, scan the code. If you can't, there's a URL. That's the test question. Ooh. As you can see, the results are displayed live, and it seems to be working pretty well so far. I thought as much. There'll be some sleepers. And I know there will also be there'll be a mischievous lot who'd like to try and break this. Please do, but leave it till the end, please. So, right, on to HPC. How many of these do you recognize? Siobhan? Ooh, people are thinking. Don't take too long. Oh, yeah, there was a 0. Where's it gone? I apologize. There was a 0. It's what? First fail. There was a 0. It's gone. I actually had put the 0 there because my children said, what is this? Not bad. I, too, only knew 1. Here we go. So the first one is the ENIAC, or whether it's pronounced ENIAC, I have no idea. Some argue that it wasn't even a supercomputer because it was based on vacuum tubes. The CDC, as some of you may have recognized that one. That CDC was the first to rely on transistors. You all will be familiar with the Apollo guidance computer, but it was the IBM 360 that managed the Apollo 11's operations and management communications back to Earth. The Cray XMP was a predecessor to the Cray 1, so it's not Cray 2, and was the first multiprocessor computer offered by Cray. The Fujitsu Wind Tunnel, now I think that's just the coolest name, was a joint project of the National Aerospace Laboratory and Fujitsu. So that's a bit of a history lesson over. Now, on to the raw processing power. As you can see, the raw processing power of these early supercomputers are now shadowed by the latest everyday and small gadgets of today. A Cray 2 was equivalent to an iPhone that is already, what, 4 or 5 years old? I'm not too sure. I'm not a fangirl of iPhones, so I don't keep up. Right, this slide does go against presentation guidelines of squashing and squeezing, but I really wanted to show this as it shows a comparison of what we have today with smartphones, watches, games console, and early supercomputers. A Sony smartwatch is more powerful than a TCM CM2, and a PlayStation 4 is more powerful than an Intel ASCII Red 1998. Crunch these numbers for a little while because there's a question coming up. So, next question. A Tianhe 2 is number 2 on the top 500 supercomputer list. These are its credentials. How many PlayStation 4s is it equivalent to? Ooh, This is good. Keep going. I'll give you a few more minutes. Shall I put you out of your suspense? It's 18,400. Not bad. People are still going. Right, yeah, yeah. Oh, yeah, yeah. Keep going. Supercomputing has been around for decades and is very much so dominated by Intel. Now, this has not been the first talk on HPC at Linaro Connect. The first was in Bangkok, where we had Eric Henneneofer from ARM Research, and then from CERN at Budapest, along with Chris Adeniyi-Jones, also from ARM, who ran a tutorial on scientific computing. Also, Fujitsu, in collaboration with Riken, shared news on the post-K supercomputer. So yes, Linaro was hinting on things to come. But why AArch64 for HPC? ARM made its first step into HPC on the Mont-Blanc Project. The Mont-Blanc Project tackled the initial work of building test systems and porting software for ARM HPC. Since then, and from work involving the US Department of Energy's, the DOE's Fast Forward 2 project, this has demonstrated that AArch64 is competitive on a per-core and per-socket basis. Furthermore, the HPC community was seeking multi-vendor options. They wanted choice. They do not want full proprietary systems which inhibit them from fixing problems they have found in, say, for example, OpenMPI, and relying on the vendor instead. And we know what the lead time for such fixes are. The ARM ecosystem brings choice and better optimized solutions. It also brings the opportunity to co-design and co-develop from architecture design right through to software. With choice, the need for standardization and platform compatibility is paramount. Technology standards such as Gen Z are inspiring the industry, but we must not forget Fortran. Yes, that still matters to HPC. With ARM's introduction of the scalar vector extension as a standard architecture, and the need for massive parallelism means changes to software, it's an opportunity to modernize software, and what better way than open source. These are some of the recent headlines, and they have demonstrated that the HPC community are taking ARM seriously. At the recent ISC 17 conference in Frankfurt, Atos announced the Bull Sequana X1310, an ARM-based variant of the company's Sequana X1000 supercomputer line. Penguin Computing also announced its own Thunder X2 powered cluster platform. The product, known as the Tundra ES Valkyrie, I'm not sure if that's pronounced correctly, can be ordered now and will ship in the third quarter of 2017. HP Enterprise unveiled the Machine, the new memory-driven computer. The GW4 Alliance, together with Cray, will be providing a Tier 2 HPC service named Isambard, after the renowned Victorian engineer Isambard Kingdom Brunel. The aim is to provide multiple advanced architectures within the same system in order to enable evaluation and comparisons across a variety and range of hardware platforms. It's all about choice. So why Linaro? HPC has a large and growing open source component. We can offer tool chains to those who want choice. We can focus engineering on library optimizations that will benefit all microarchitectures. It's a place where SoCs, system vendors, system integrators, users, distros, hyperscalers can co-develop and root the foundational software to make choice easier for the desired application space. From this, the support of members, a special interest group was formed. This was formed under the existing enterprise segment group, LEG. We currently have 7 members: ARM, Cavium, Fujitsu, HiSilicon, Washington, and Qualcomm, and Red Hat. They form the steering committee. We also have CERN and Riken on board, on the advisory board. They provide subject matter experience and guidance as users. User feedback is important. It's not just about SOC enablement. We need to get user feedback. This will help us drive the engineering in the right direction and ensure that the application space is ready for when silicon lands. We are working towards optimization, standardization, interoperability, modularization, and orchestration. That's a lot of words. We want to lower deployment barriers and management barriers by leveraging the Linaro Developer Cloud and other services to develop cost-effective, cloud-based HPC development frameworks. HPC environments are hard to come by. They're expensive, and the Developer Cloud will provide instances of HPC environments to give access to developers to hardware that they can start developing the applications on. The data-driven economy is a boom. Machine learning and deep learning are both critical to the future of HPC, also mentioned by George yesterday, specifically as a path towards exascale computing. Driving engineering in HPDA and machine learning will aid the success of organizations to fully capitalize these technologies. This slide has got lots of information on there. It gives an idea of the breadth of scope in the HPC SIG. The items in color have been prioritized and is what we are working on at the moment. Note the colors do not signify anything. I've just highlighted those to present what we're working on currently. There really is a lot to do in this space. So to start, we are working on getting ARM enabled on OpenHPC. I'm going to let Renato Golin, who is the tech lead in HPC, talk a little bit about this. Where is Renato?
Thank you. It is. So OpenHPC is it's a package management. It's an external package repository that we have packages that help you set up OpenHPC or HPC clusters. So instead of trying to find which package merges with another package and which component works with another component, we get all of these components and we test them on ARM and other people on Intel, and we make sure that these things work out of the box. And for that, we write recipes and documents that will help you to just follow the guidelines, copy and paste shell commands, and then you have a HPC cluster at the end of it. And in Linaro, we're working to automate these further and then to press a button and have a cluster at the end. The latest release is 1.3.2. We validated this with the ERP kernel in some machines, with the standard CentOS kernel in other machines, all of them ARM, of course. And this is still in tech preview for ARM because some of the things don't work out of the box. So that's one work that Linaro is doing, which is to talk to the communities that will make this be out of the box. And next slide. So if you see at the top left, OpenHPC, we actually have two mentalities about this. One of them is the things that should just work, and the other ones are the things that should just work as well, but you can customize. So for instance, basic infrastructure packages like Werewolf, that they provision the nodes, and Slum and MERS, that they dispatch jobs, and InfiniBand and disks, they should just work. So you run the recipe and you have a cluster at the end with all of these things already installed. You don't really care much how performing because they're really not in the critical path. But then you have all the applications and libraries and tool chains and that you want to use out of the box to see if it works, but you also want to fiddle with it, you want to change components, you want to choose different libraries. So OpenHPC allows you to choose a specific tool chain with a specific MPI implementation as a default, so when you just like compile stuff, you run make, everything works fine. And so that helps us tune specific parts. So you install the whole HPC, OpenHPC, and then you just start fiddling with one library and running benchmarks, etc. This is good for us to fix bugs and make them faster, but it's also good for the users that will then be able to have their own custom version and install a package and recompile from source and apply patches and etc.
Great. Thank you, Renato. So, I figured you were waiting for the next question, so. Have you been involved in deep learning? Ooh. We know that, Mark. As mentioned before, the data-driven economy is in boom. And machine learning and deep learning is making an impact in HPC too. But first, I want to make clear some terminology. And here's a question for you. Machine learning, in simple terms, is programming a machine to then go and learn itself. There are many methods of learning. In supervised learning, oh, it's okay. You could leave it back on that question, it's fine. In supervised learning, the users train the program to generate an answer based on a known and labeled data set. Neural networks use supervised learning, in which inputs and outputs are known, and a goal is to build a representation of a function that will approximate the input to output mapping. In unsupervised machine learning, the algorithms generate answers to unknown and unlabeled data. Reinforcement learning allows the machine or software agent to learn its behavior based on feedback from the environment. This behavior can be learnt once and for all, or keep on adapting as time goes by. This is done through a method of rewarding. Evolutionary algorithms, such as genetic algorithms and genetic programming, allow you to explore a space of parameters to find solutions. It's a landscape of solutions that score well according to a fitness function. Solutions are encoded and pitted against one another in a manner comparable to natural selection, where the best solutions survive to cross over and produce new solutions for evaluation. So how does this fit with HPC? HPC was traditionally used by researchers for simulations, and well, machine learning really took off once we realized GPUs were great at executing machine learning techniques. And we started to see real results very quickly as well. HPC offers the opportunity to accelerate performance and deepen understanding of large data sets through machine learning, through parallelism, and methods of exploiting data parallelism. This will allow training of models over larger data sets and over quicker iterations. We are now at a point where we consider supercomputers designed for both computational science as well as machine learning. So it seems that we do have a fair few in the audience who have been involved in deep learning. That's really good, and I'd like to see that within the next few Connects we have more and more people who are involved. So, next question. Yes. Great. Yes. Who's that one? Was that you, Mark? Is that Maxime? No. I'll have a word with you later. So, Siobhan, leave that question up, but we'll go on to the next slide. Leave that one there. So, what about artificial intelligence? For me, yes, the AI term is being diluted. I'm a purist, I'm a traditionalist. And therefore, true AI means replicating many aspects of human intelligence and become an entity on its own right. Tesla's theorem, intelligence is what machines haven't done yet. Note, if you Google Tesla's theorem on the internet, it will come up as AI is something that hasn't been done yet. That's not quite right. He's been misquoted several occasions, and he's tried to rectify that. But as we know with the internet, once it's out there, it's gone. There's nothing you can do about it. There's so much more that needs to be untapped and solved before we could say we have reached true AI. There is emotional intelligence, social intelligence, to name a few. The fundamentals of human intelligence is self-preservation. Is that what we want in AI? We have to ask ourselves. Machine learning algorithms take time to get right too. Those that are out there have issues too. Here is one example of many from Google, where they designed a neural network that thought dumbbells looked like that, with an arm to go with it. It could not determine that actually that's an arm and that's a dumbbell. It failed to completely distinguish that. So coming back to HPC, with a data-driven economy, HPC is no longer an exclusive domain for science labs, but it's becoming mainstream. HPC brings the benefits of advanced algorithms to users at scale. Data centers will also have HPC environments. But then HPC environments are expensive, and to make them more accessible, there are now many HPC cloud service providers. But these come at a cost too. And as a result, we explore containers. Containers work on bare metal, and clouds provide flexibility in management of workloads. They allow for a varied setup for different applications. They make migration to newer software versions easier and less impact on production systems. With these new approaches, we have to consider where the data lives. For scientific computing, on the other hand, petaflops was yesterday's news. There is a big movement to exascale computing, exaflops. With that comes challenges also. What architecture is going to cut it? As a result, some of the research labs are looking for co-design. How do we scale? Simply scaling from today's requirements for a petaflop computer, the exaflop in 2020 would require 200 megawatts. That doesn't scale. Memory bandwidth and capacity are not keeping pace with the increase in flops. Decreasing clock frequencies to conserve power will mean the number of processing units on a single chip will have to increase. This means exascale architectures will likely be highly concurrent. The cost of data movement is also very high and needs to be minimized. And then there's always, what about compilers, the changes that will be required to support this in compilers? Which leads us to another realm, quantum computing. Paul Benioff first applied quantum theory to computers in 1981. They work on the qubit, which unlike traditional computers who focus on binary 0 and 1s, the qubit focuses on 0 or 1 and on both simultaneously. It has a state where it can be in both states. The notion is that a qubit represents subatomic particles that have a superposition state also. They say that this will potentially be millions of times more powerful than current supercomputers. And at one point, quantum computers would replace silicon chips. D-Wave have already created a quantum computer, and I've provided a link. The chip in the slide set is from the D-Wave quantum computer. We saw this in ICS, and it just looks beautiful. I've also provided some recent headlines that were publicized around quantum computing. IBM makes a breakthrough in quantum computing. And the second one is a bit of a clickbait. Scientists try to speed up the internet with, yeah, right. But there is good information in that slide. It is a very exciting space. And I have to ask myself, could quantum get us true AI? So I pose that question to you. Will we ever get true AI? Leave that question up. So this is a call of those who would like to develop and take part in the HPC engineering that Linaro is working in. There are some links here. ARM have a good repo. There is a link to the developer cloud where we are setting up HPC instances. There's a link to the Open HPC project. They have an abundant amount of issues, and we could do with help for anyone who wants to participate. It's an open project. Anyone can participate. Also on GitHub, there's a whole repo on machine learning for those who want to dabble in deep learning, machine learning techniques. And there are also talks today, which are very related to HPC. There's a RAS talk on ARM64. And tomorrow, there's a talk on vector optimizations for glibc, benchmarking in the toolchain working group. On Thursday is the data center day, so we are running a HPC BOF where we're focusing on what is required to make HPC development easy and what are the obstacles we need to overcome. Also on Thursday, we have Riken presenting an overview of the post-case supercomputer. And on Friday, there's a talk on deep learning on ARM platforms. So do join in. If you are interested and feel you have a side project and would like to just engage, just please speak to Renato or myself, and we can direct you accordingly. On that note, thank you. I'm glad the poll seemed to work. And it was 50-50 about whether we will get true AI. That's interesting. Thank you.